Torque, as the book will say, rhymes with fork or cork. But it's a twisting effect caused by a force and a lever. Now we can use this equation to calculate torque. We will use capital T for torque. Torque is the force perpendicular times the distance or length of the lever arm. So T stands for torque. The units will be Newton meters. In English, it's foot-pounds, but we're going to be using Newton meters. You could also use Newton centimeters. F, or F perpendicular, symbol for perpendicular, perpendicular force will be measured in newtons, and D will be the length of the lever arm in meters. Once again, you could use centimeters, but the standard here will be meters. There are two directions to torque. It is a vector. There's clockwise, CW, obviously, and then counterclockwise, CCW. So that's pretty easy to keep track of. Clockwise is the way the hands of a clock travel, counterclockwise the other way. So here's an example. We use torque to tighten nuts and bolts, or to loosen them. In this case, we will be loosening this nut. I'll highlight the nut in blue, because the applied force here will make the whole thing rotate counterclockwise. Some people use the acronym lefty-loosey, righty-tighty, if that works for you, but in this case, counterclockwise is what loosens nuts, clockwise tightens them. Anyway, to calculate the torque here, it's just torque equals the force perpendicular times the distance. If the force is not perpendicular, you have to make adjustments by measuring the angles and doing some other things, but we're not going to consider that just yet. We will be doing all problems where the force is perpendicular to the lever. So it's a pretty straightforward problem in this case. The applied force here is 20 newtons, and the distance is 0.30 meters. So the torque is 6.0 Newton meters, not newtons per meter, but Newton meters, and this is CCW, counterclockwise. We'll be loosening this nut. We could have left the problem in centimeters, in which case you would have ended up with 600 Newton centimeters of counterclockwise torque. That would be perfectly acceptable as well, but the standard is Newton meters. Equilibrium, or balance, in regards to torque. We already need our net forces to be zero. I'll give you that example, but we also need our torque net to be zero. In other words, our clockwise torque needs to be equal to our counterclockwise torque. It says counterclockwise torque. Here's an example with a teeter-totter, old school teeter-totter. So these two kids are sitting on this teeter-totter, and let's say that the girl has a weight, well, just around 50 pounds, but let's put this in newtons. She's about 250 newtons, and she's sitting at the end of the teeter-totter. But the boy, 250 newtons, is a little heavier, so he cannot sit at the end. If he sits at the end, and if the teeter-totter is dead center on the fulcrum, the log there, the rotation point, then he must scoot in a little bit. So he's not sitting quite in the end, as you'll see in a second here, or you can see in the picture as well. Let's say he's a little heavier. He's around 80 pounds, which is about 350 newtons. Let me simplify the diagram. In these torque problems, what I typically do is I'll draw the diagram, simplified version, free body force diagram. There's the teeter-totter over here on the right. The girl is 250 newtons. The boy is sitting in from the end a little bit. He's 350 newtons. The rotation point here, the fulcrum, where the log is right now, there must be a support force. And if we're ignoring the weight of the board right now, which we will do in this problem, but the next problem will factor in the weight of the board itself, the upward force here must be 350 plus 250, which is 600 newtons. Not that important right now, but it will come into play later on. Anyway, in this particular case, there are three locations where forces are attached. I'll highlight those with blue dots. I'm going to call those points A, B, and C. Let's also say that the girl is 1.8 meters away from the rotation or the center of the board. The board is, say, 3.6 meters long total. But the boy is scooched in a little bit. He's not all the way to the end. So from B to C, we don't know what that is. I'm going to call that D2. And I want to calculate my torques with respect to point B in this case. So let me write that down. Point B is the location from which I'm going to calculate my torques. I want my clockwise torque to be equal to my counterclockwise torque. Now, let's practice our clockwise and counterclockwise for a few minutes. If point B is stationary and everything is rotating about point B, and we call that the fulcrum in this case where it's rotating, the boy is making the teeter-totter go down at point C. That makes the teeter-totter rotate, in effect, clockwise. So the boy is creating the clockwise torque with his weight. So that comes down to this equation over here. I'll do this in blue now. His force is 350 newtons. That's the force, times his distance from the fulcrum. Measure everything from point B to point C in this case. That's our unknown D2. We don't know what that is. We're going to figure that out. The counterclockwise torque is where the girl's force pushing down, making the whole thing, trying to rotate counterclockwise. Now, this board is in balance. That's why I can use this equation here at the bottom. Her weight, or force, is 250 newtons times her distance, which is 1.8 meters. So the only unknown here is D2. If I calculate that, D2 comes out to be 1.3 meters. So he is 1.3 meters from the center of the board, or you can put it another way, he's 0.5 meters from the end if there's 1.8 meters of board on either side of point B. So he's a half a meter in, he's 50 centimeters from the end of the board. He has to scooch in to keep this thing balanced. Teeter-totter problem number 2. Same girl sitting at the end on this teeter-totter. She's sitting at the end, and she is still 250 newtons, which is just under 60 pounds. Now we have a littler boy over here at the end, and he's 200 newtons, let's say. Let me simplify the diagram, which I like to do, which I recommend that you do when you do these problems. Here's a teeter-totter. Here's the 250 pound, or 250 Newton girl, one end, the 200 Newton boy at the other end, and now we cannot ignore the weight of the board. Let's say the board in this case is 100 newtons. In the previous problem we could ignore it just for simplicity's sake, but also because it was in the center where the fulcrum was and it did not really affect the problem. But here the weight of the board will affect where the whole thing balances. Now, combining this with what we learned in class about center of gravity, and assuming this is a uniform board, which it is a good assumption, you put the entire weight of an object at its center of gravity. The center of gravity of a board is geometrically in its center. If this board is 3.6 meters long, like it was in the previous problem, that little arrow I just drew there is the weight vector for the board, 100 newtons, placed at the center of gravity of the board, dead center geometrically for the board. Now the log itself, the fulcrum, I'll use a different color just for that, is supporting everything here if we balance out the torques, which is what we want to do. Their feet are not touching the ground. That weight vector holds everything up. It's going to be the sum of the three downward vectors because we need to have F net equal to 0 in addition to the torque canceling out to 0. So that is what? 550 newtons of support, 550 newtons. And now I have three forces. I'm going to highlight their locations, 1, 2, 3, 4 with blue. I'm going to call those points A, B, C, and D. And I know some of the distances. I know from A to C is 1.8 meters. That's the 1.8 meters. It's the same board as it was before. And also from C to D, because point C is the midpoint of the board, that's 1.8 meters. We just do not know where point B is yet, and that's what the problem is going to be, is like, where is point B? Where does this board balance? That's the question that we're going to answer here. Where does the board balance? The teeter-totter or board Where does the board balance? All right, now follow me here because this is where it gets a little difficult. I am going to calculate my torque with respect to point A. And the reason I do not want to pick point B as my reference point, which is tempting to do because that's where the actual rotation is. But what you'll find here is that you can pick any point, A, B, C, or D, to calculate your torques and balance the torques out. The reason why you don't want to pick point B is because you don't know the location of point B. You don't know where it's at. And that will make the problem very, very difficult, even though it's tempting to use point B as you can see it's the actual rotation. We can treat it as if point A is the rotation or torque reference point. For example, I'm still going to have the clockwise torque equal to the counterclockwise torque. If you pick point A as a fixed point, like the center of a clock, and the horizontal red beam here, board, is like the second hand of a clock, if you pull down on point C or point D, either one of those, that will make this board or needle rotate clockwise. So the 100 Newton and the 200 Newton forces both are contributing to clockwise torque, but they have different distances. So for example, from point C, it's a 100 Newton force, and we're calculating everything with respect to point A, so we need to measure to point A from point C, which is 1.8 meters. So with reference to point A, the force at point C, the 100 newtons, is 1.8 meters away. So the torque it generates with respect to point A is 100 times 1.8, the force times the distance. But I have to add to that the torque that's produced by the 200 Newton force at point D. That's 200 newtons times 3.6 meters. That's how far it is from point A. Those are both trying to make the board rotate clockwise if we're holding point A stationary and letting point B drop. So kind of ignore the log right now. We'll practice this some more. But anyways, now the counterclockwise torque with respect to point A. That's the blue force, the 550 Newton force of the log pushing up. That would push the whole thing counterclockwise. It'd be a 550 Newton force times a distance that we do not know. That's what we're looking for. Let me label the diagram here. That's D. That's what I'm looking for. How far it is from point A to point B. Because I'm measuring everything from point A right now. Alright, so that's my D, my unknown. Now I have the math figured out. That's the hardest part right there, that statement, and figuring out the clockwise versus the counterclockwise. We'll practice that. Anyway, we have 180 plus, I believe, 720 equals 550D. It's 550D. So that's 900 equals 550D. So D equals 1.6 meters. That's where the fulcrum or the log is, 1.6 meters from point A, which would be 0.2 meters from point C. Here's the alternate approach to problem number 3. If I had picked point C as my initial reference point, let's make believe I didn't know the answer was 1.6 meters. Once again, if you try to approach this problem by picking point B to calculate your torques, it's going to be a nightmare because you don't know how far points A, C, or D are from point B. But let's practice this again. If I'm doing another version, another solution, balancing the torques with reference to point C. For example, when I say reference to point C, or any point, we're holding that point stationary and letting everything rotate around there. So you can ignore the actual log and the girls. Make believe like point C is the center of a clock, and that horizontal red line through point C is the second hand that can rotate clockwise or counterclockwise. Once again, with reference to that point, I forgot to mention for the previous part, point A, the force that's applied there, in this case the 100 newtons, that does not generate any torque because it has no distance from point C. Just like in the above part, the red solution from point A, the 250 newtons never came into play because that does not generate torque with reference to the point you picked. So we're not going to use the 100 Newton force this time. But anyways, with reference to point C, which of the forces, the other ones, the 250, the 550, or the 200, are trying to make everything rotate clockwise with respect to point C? Well, that would be the 200 newtons at point D. That's generating clockwise rotation if we hold point C fixed and let everything rotate around point C. So that'll be a force of 200 newtons times the distance from D to C now. Measure everything to C. That's 1.8 meters. Plus, the 550 is also, that's 550, trying to make the whole thing rotate clockwise. Now I have a new distance though. I'm not using this same distance. Now I'm using this, I'm going to call this D2. That's the separation from points B to C. Let's call this other one D1. D1 was 1.6 meters. This is D2 now, from B to C. So 550 times D2, which I do not know how far point B is from point C, but pushing up at point B will make the whole thing rotate around point C if C is fixed and everything else moves, equals the counterclockwise torque. In this case, it will be the 250 Newton force that's trying to make everything rotate counterclockwise around point C. 250 times the 1.8 meters that force is from point C. That's the distance from A to C. Once again, the hard part's done now. If you do the math here, you have 360 plus 550 D2 equals 450. If you subtract the 360 from both sides, divide by the 550, you end up with D2 equals 0.2 meters. Now, is that a different answer than we got? It looks like the other answer we had is D was equal to 1.6. Well, the D1 was from the girl from A to B is 1.6. Now we're getting that D2 from B to C is 0.2. This is consistent because what do you notice about D1 plus D2? Well, that's 1.8 meters. That's half the board. From A to B to C, it's 1.8 meters. So that's consistent. That's an alternate solution to the problem. You don't need to do the problem two different ways. You could actually do this problem from point D as well. I'm not going to do a third solution, but it will give you the same answer no matter which point you pick, even if you pick point B, but it will be very, very difficult to do this problem from point B as I mentioned.